Welcome back, everyone. So last time we covered the theory of the scalar product. Today, we're getting our hands dirty. We're going to take that theory and put it to the test with some real, challenging A-level exam-style questions. Let's get into it.
All right, here's the game plan. We'll do a quick recap, then a warm-up with some core calculations. After that, it's the main event, some tough 3D geometry. We'll also touch on a key vector rule and wrap up with your new problem-solving toolkit. Sound good? Let's go.
Okay, Section 1, a quick recap. Let's just refresh our memory on the scalar product, the dot product.
Right, so remember the dot product has these two sides to it, right? Two different faces. You've got the geometric form, which is all about the angle between the vectors, and then you've got the component form, which is just pure calculation. The real trick, the secret sauce, is knowing which one to use and when. We're going to be jumping back and forth between these two a lot today, you'll see.
All right, time for a warm-up. Let's get the brain in gear with some quick-fire questions. I'll pop a question on screen, and if you're feeling brave, hit pause and give it a shot yourself before I walk you through it.
Okay, first one. A nice, simple 2D calculation to get things rolling. What's the scalar product of vector A and vector B?
Easy peasy, right? We're just using that component formula. We multiply the x's together, so that's 3 times 1, and then we multiply the y's together, 4 times 2. Add them up, 3 plus 8 gives us 11. Boom, done.
Okay, next up. How do we figure out if two vectors are perpendicular? You know the fancy word for it is orthogonal. What's the test?
So here's the absolute golden rule. If two vectors are orthogonal, their dot product is 0. No exceptions. It's because cos of 90 degrees is 0, right? So let's check these two. We do 1 times 3 plus 2 times negative 1 plus 2 times 4. That's 3 minus 2 plus 8, which is 9. Is that 0? Nope. So these vectors are not orthogonal. Simple as that.
Okay, what about this one? We've got two vectors, and they're sitting right on the axes. You can probably even picture this in your head, right? What's the angle between them?
Let's work it out. The dot product is 5 times 0 plus 0 times 3, which is just 0. And right there, we can stop. If the dot product is 0, we know immediately the angle has to be 90 degrees. This is a perfect example of how those two formulas are linked. The dot product is the numerator in the angle formula, so if it's 0, the whole thing is 0, and the angle must be 90.
Okay, warm-up is over. Time for the main event. We're diving into the deep end now, applying the scalar product to some really tricky 3D geometry problems from exercise 9C. This is where it gets fun.
So here's our first big challenge, question 5. We've got this cuboid, and we need to find the angle NPM. Now look, whenever you see a 3D shaped problem, what's the very first thing you should do? You have to turn the geometry into coordinates. You got to give it an address. So we'll pick a corner, call it the origin, and lay down our x, y, and z axes. That's always step 1.
So here's how we attack it. First, we need the two vectors that make our angle. In this case, that's the vector from P to N and the vector from P to M. Once we have their components, it's just a process. Step 2, calculate their dot product. You can see it comes out to -4. Step 3, find their magnitudes, which are root 13 and root 8. And finally, step 4, you just jam all those numbers into the cosine formula. That's it.
And when you punch that into the calculator, you get about 113 degrees. Remember how our dot product was negative? That was a dead giveaway that we were going to get an obtuse angle, something bigger than 90. It all connects.
Okay, this next one from question 8 is really cool. We need the angle between vectors OM and NG. But wait a second, if you look closely at the cube, those two lines don't even touch. They're what we call skew lines. So how can there be an angle between them? Well, vectors don't care about position, only direction, so we can still find the angle between their directions using the exact same method. Pretty neat, huh?
The recipe is exactly the same. We figure out the coordinates for all the points we need, build our vectors OM and NG. You can see them there in IJK form. We calculate the dot product, which is a nice positive 20. We find the magnitudes, 6 and root 41. And we throw it all into the formula. The result? An angle of about 58.7 degrees.
All right, our last big challenge, question 10, is a pyramid problem. And this one is a little different. It's more like a detective story. We're given some clues, and we have to use the properties of the dot product, specifically that orthogonal rule, to hunt down the location of an unknown point P.
So how do we crack this? The biggest clue is that we're told there's a right angle at N.
That should make a light bulb go off in your head. Right angle means orthogonal vectors. Orthogonal vectors mean the dot product is 0. So we know that the vector np dotted with the vector nm must equal 0. Now we don't know where p is, but we know it's on that vertical line, so its coordinates are just 0, 0, t. We're solving for t, so we create our vectors using t, set their dot product to 0, and bam, we have an equation. We solve for t, and it turns out to be 2.5. So the position vector of p is just 2.5k.
Okay, before we get to the summary, let's just take a quick detour. This is a really important conceptual point about vector rules that you need to get right.
You might see a question like this that's designed to trip you up. Why can't you just dot 3 vectors together? What's actually wrong with the expression A dot B dot C? The reason is all about what comes out of the operation. When you dot 2 vectors, like A dot B, the answer isn't another vector. It's a scalar. It's just a number. So then the expression becomes a number dotted with vector C. And you can't do that. You can't dot a number with a vector. The operation just isn't defined. It's like trying to multiply a word by a color. It just doesn't make sense.
All right, let's wrap this up by looking at what we've added to our problem-solving toolkit today. What can you actually do with the scalar product? So, here's the deal. The scalar product is so much more than a formula. It's your key to unlocking all sorts of things. You can now find the angle between any two vectors in 2D or 3D. You have a super fast test for telling if things are perpendicular. You can even hunt down unknown coordinates inside complex shapes like pyramids. It's basically a bridge that turns messy geometry into clean algebra. And there you have it, the real power of the scalar product in action. But let's end with a final question to get you thinking. We've got the angle between two lines nailed down, but what about the next level? How could you use what we've learned today to find the angle between a line and a plane? Something to chew on. Thanks for watching.